Computer chips power our digital world. They are in our phones, cars, and even refrigerators. These tiny squares are marvels of engineering. Each chip is a miniature city, bustling with activity. Imagine billions of transistors connected by a network of microscopic wires. These wires can stretch for hundreds of kilometers if laid end to end. The transistors act as tiny switches, turning the flow of electricity on and off. They are the building blocks of digital logic. The speed at which these transistors switch determines the processing power of a chip. Modern transistors are incredibly small, measuring just a few nanometers across. To give you an idea of scale, a single human hair is about 80,000 nanometers wide. On a modern chip, billions of transistors fit into an area smaller than a fingernail. This density of components is what allows for the incredible processing power we see in today's devices. Creating these intricate circuits requires a process called photolithography. Imagine using light to paint a circuit diagram onto a silicon wafer. This wafer, typically made of ultra-pure silicon, acts as the foundation for the chip. The process begins with cleaning the wafer to remove any impurities. It is then heated in an oxygen furnace. This forms a thin layer of silicon dioxide on the surface. Next, a light-sensitive material called photoresist is applied to the wafer. This material is spun at high speed to create an even coating. The wafer is then baked to harden the photoresist. Now comes the crucial part: exposure to ultraviolet UV light. A mask, essentially a stencil of the circuit pattern, is placed over the wafer. UV light shines through the mask, exposing specific areas of the photoresist. The exposed areas become chemically weakened. After exposure, the wafer is washed in a chemical solution. This solution removes the weakened photoresist, revealing the underlying silicon dioxide layer. The exposed silicon dioxide is then etched away using chemicals or plasma. This creates the desired pattern on the wafer. To create the transistors, a process called ion implantation is used. In this process, ions of specific elements, such as boron or phosphorus, are bombarded onto the wafer. These ions embed themselves in the silicon, altering its electrical properties. This is how positive and negative regions, essential for transistor function, are created. The entire process, from photoresist application to etching, is repeated multiple times. Each cycle adds a new layer to the chip, building up the complex three-dimensional structure of the circuit. Between each layer, the wafer undergoes a process called chemical mechanical polishing, CMP. CMP uses a slurry of abrasive chemicals to polish the wafer to an atomically flat surface. This ensures that each layer aligns perfectly with the one below it. While microchips are marvels of engineering, their production comes at an environmental cost. Manufacturing these intricate devices requires a significant amount of energy and resources. The fabrication process uses vast amounts of water for cleaning and cooling. Specialized chemicals, some of which are hazardous, are also used in large quantities. The industry is aware of these challenges and is actively seeking solutions. Companies are investing in more energy-efficient equipment and processes. Recycling and water conservation efforts are also increasing. Researchers are exploring new materials and manufacturing techniques that have a lower environmental impact. The goal is to create a more sustainable future for microchip production. As technology advances and demand for chips continues to grow, finding ways to minimize the environmental footprint of this industry will be crucial.